All right. Next up, we have Kevin Grigorenko with Linux core dumps. Please give him a warm ToorCon welcome.
All right, hey everyone. I'm going to fly through these slides. I've included my email here, and I'll include a link to the slides at the end. So some of these will be very quick, but if you have any questions or want to dive deeper. So core dumps. Many interactions with core dumps are there's a crash, and maybe it goes to some systemd core dump, maybe it goes to abort D, maybe it goes to the working directory, and somebody sees a 4 GB file and says ACK and removes it. I said many. A lot of you maybe have never even seen a core dump. That's because most interactions with core dumps are process crashes, the core U limit is 0, and poof, the core is gone. Or maybe the process U limit's okay, but it goes to one of those services and then goes to some disk somewhere that nobody ever looks at. Similarly, when a kernel crashes and wants to create a VM core, kdump often isn't configured. Again, poof, it's gone. So why should you care? Crashes are problems. It's kind of obvious, but especially for this audience, they may be symptoms of somebody trying to hack a system. They may simply be application bugs, but that can also mean data corruption for users. And when a process crashes, any outstanding work will die. Oftentimes you don't have automatic restarts, and so your service may be unavailable. If you do, that actually gives a hacker opportunity to try other ways of crashing and other vulnerabilities. So the kind of summary of this talk is we shouldn't be scared of core dumps. When a dog poops in your house, we don't just rm-f the poop. We try to figure it out and how to avoid it in the future. So what is a core dump? It's just a file. It includes virtual memory of the process or kernel. It may include register values and other metadata. So a process or user land core dump represents the state of a particular process, and a kernel core dump represents the state of the kernel. It's an ELF formatted file, so just like a program, so we can use GDB on it. And just a quick diagram of process creates core, kernel creates VM core. It's kind of basic, but we're going to be talking a lot about virtual memory. What is virtual memory? It's just an abstraction over RAM or swap. It simplifies programming, and also for user programs, it isolates them from each other in general. And then the kernel or the processor translate a virtual address to a physical location. So in this diagram, we see a 64-bit address space, which is what the program is dealing with, and then address references will be converted to RAM or swap references on the right. How much virtual memory is being used? Simple, use PS or a similar tool. VSC is the virtual size, and RSS is the resident set size. So in the diagram below, all of the allocations made by the program are the virtual size. That's going to be within that process. And what subset of that are actually resident in physical memory is the resident set size. So in this example, we have 2 virtual allocations, and they point to 2 pages in RAM that are resident. However, you can't just sum up resident size across processes because pages may be shared in RAM. So how much virtual memory is actually being used by a program? How do we break that down? If you cat/proc/pid/smaps, you get every virtual memory area, or VMA. This is how the kernel breaks down memory into chunks in general. And it'll tell you the range of the VMA, the permissions from the program point of view, if it's a file, which file path it is, and it will also show how much of that VMA is resident and how much, and PSS is the proportional set size. That's the amount of resident set size divided by the number of processes sharing pages within that VMA. So that's a good way to actually size your system. This is a very dense slide. I'm not going to go through in much detail, but how does a program get virtual memory? In general, it'll either use malloc or mmap. So we'll take a simple case, and if we start with the program in the top left in blue, and it makes an mmap call. That goes straight to the kernel. It's a system call, and the kernel will give it back a chunk of data. Now, mmap is generally used for large allocations. That's because however much you request will be rounded up to the page size. Also, that entire amount will be zeroed out, so it has a cost. But however, you're probably more familiar with malloc. Malloc is more often used for small-ish allocations. So when the program calls malloc, by the most common malloc implementation is glibc malloc, and it actually has a pretty complex algorithm. If the size that you're requesting is less than a sliding threshold, then we go down the yes path on the right. And that will actually go and grab chunks either from the OS through sbreak, and that's what you commonly think of as the data segment, or in more recent versions, to avoid cross-thread contention for malloc, it will actually mmap other chunks that it calls arenas, and it'll grab the piece of memory to satisfy your request from either the data segment or the arenas. Oh, and I didn't mention, so if the size is greater than the threshold, even though you called malloc, it will actually call mmap. And similarly with free, it will un-mmap it. Here's a 32-bit virtual memory layout for Linux. On the left is the most common on a 32-bit kernel. The top gigabyte is reserved for the kernel, and the user space basically has 3 gigabytes. And the data segment and the program are going to be towards the bottom, and then mmap, shared libraries, thread stacks will be at the top, growing towards each other. If you're running a 32-bit program in a 64-bit kernel, you'll actually get all 4 gigabytes. There's also a huge mem kernel, which can be done on 32-bit, although that's rarely used. On 64-bit, it will depend on your physical processor. On x86 64, it supports up to 256 terabytes of virtual memory, 128 terabytes for the program, and 128 terabytes for the kernel. And that's why if you do ls/proc/kcore, you'll see 128 terabytes. So before we go into how to get core dumps, it's kind of boring, even though I think that's critical and actually where we're dropping the ball. Because that's kind of boring, let's assume we have a core dump. So if you just have a core dump, it's an ELF formatted file. And so that in the diagram shows an ELF file, which is some description about it, metadata, which will have some notes about the core, and then the actual virtual memory that was dumped. So we could do readelf-h on the core and see that it is a core. So next we'll need to see which program caused the crash. If we do readelf-n, we'll get the notes. And in the notes, it'll show mapped files, and usually the first mapped file is the program. In this case, we have /work/ToorCon/a.out is the program that caused the crash. So now that we know what the program is, we can use GDB, for example, to load both the program and the core. And what I've highlighted in red are first sigsec-v, that's what caused the crash. The second is strlen, that's where the crash occurred, the top stack frame. And also, glibc is nice to tell you if you're missing any symbols of any shared libraries, how to actually install those symbols in some cases. And then you get a prompt, and in that prompt you can type help to get a list of commands or quit. So debugging core dumps. I love this little comic. Somebody comes in the door and says, developer, something's wrong. Developer says, stack tracer GTFO. The person says, but please help, I have this other information, stack trace or GTFO. Developers generally need stack traces, so even if you're a system admin and you aren't the developer, if you could just load that core dump, get the backtrace, you're very likely to help the developer. So BT is the command to do a backtrace of the current thread that caused the crash. And in this case, we have 3 frames, stringlen, which is what we saw earlier, puts called stringlen, and main called puts. That's the stack. And if you want to get all stacks of all threads, you do thread apply all BT. So one thing you're kind of noticing there, they're human readable names. Those are either exported functions or in more detail symbols. So symbols are basically a mapping of virtual addresses in the compiled code to human understandable parts of the code. So in the diagram, we have some source code. Let's say there's a method foo with a parameter called bar. That gets compiled. And by default, that left arrow shows that the symbols will be stripped other than the exported functions. And in the third bullet there, I have that -G, which ensures symbols are produced, doesn't affect optimization. So the documentation says we recommend that you always use -G whenever you compile a program. And that's the middle box, the green box, where we use -G, the symbols are put inside the binary. Now that can increase the size of the binary, and that's why most Linux distributions will not ship symbols with the libraries. And that's why you usually have to install debug info or, on other OS's separate symbol files. You can also do that yourself when you're building a program. So when debugging core dump, it's often best to debug it on the system where the crash occurred because it can load all the libraries. But that's not necessary. You can grab all of the shared libraries, the program and the core, expand them out into a similar directory structure on another machine, and then use these GDB parameters to load in the same way. So you can query the virtual memory. Earlier I showed /proc/smaps, which shows the VMAs. You can get similar information with info files. This will generally give just a subset of all the VMAs because not all VMAs are dumped. But this is a great way to tell about how much memory the program is using. So some simple commands. You can switch frames within a thread stack by saying frame and the number. So in this case, we switched to frame 2, and that shows us the main function. It shows us the values of the arguments, in this case argc is 3, and there's an argv, which are the command line. And it also shows us the line, because this was with -G, where the crash occurred. In this case, it's line 6 printf, and it's that variable p. So we can print p. This is more something a developer would do, maybe. And we see the value 0, and so it's a null. That's why it crashed. But also we can look at, if we have symbols, we can look at just about anything else there. In this case, we'll look at argv. If we do p-type, we see what kind of variable it is. It's a pointer to an array of strings. And so we can actually print those strings directly, and that's the command line. So now finally getting to the boring part. How do we get core dumps? This is where we normally fail. So we have to ensure that the ulimits for core and file are unlimited. By default, in most recent versions of Linux, the core is set to 0, and that's why you won't often get cores. Ulimits may be either soft or hard. Basically, hard can only be set by root. And you can query with ulimit-c-f. In this case, we see the core is 0, so core will not be produced. You can also show the limits of a running process with cat/pid/limits. Ulimits may be set in limits.conf. And in this example, on the third bullet, we can set for all users, for both soft and hard, the core and file ulimits to unlimited. Or alternatively, within the shell where the program is started, you can run the ulimit command and set unlimited for both of those. Systemd starter processes make this a little bit easier with some specific configuration. What produces a core dump? There are certain signals that will produce a core dump, whether you send those directly with kill or whether the program execution causes those signals, like a null pointer. But you can also manually request a core dump with gcore, which is part of GDB. Just to note that this attaches GDB, dumps memory, and then detaches. So it will allow the program to continue, but it's different code than the kernel, so you may get different output, even though the core format is the same. Where is the core dump? That's controlled by kernel.core pattern. And if the first so you can just set that to a directory and the name of the core with a pattern like adding the PID or the time. But if it starts with a pipe, then that'll be sent to a program. This is how most Linux systems are configured. And in this case, we see that it's configured to send the core to systemd core dump. This is assuming the core ulimit is unlimited. So what's in a user core dump? The memory dumped is controlled by core dump filter. In general, the default's okay, but there are some things that will never be dumped. So systemd core dump is the more recent core dump handler. It's configured in this systemd coredump.conf. And the defaults are pretty good, but it will limit how much disk space the cores will use. And it'll put them in varlib systemd core dump. Abort D is an older one. That one, unfortunately, has bad defaults. It will not dump anything more than a gigabyte. So we often see problems where we go to a customer and the core dump is truncated and we can't really do much. So check that on your system if you have that. In GDB, we can read memory with the X command, and just print from a starting address how many bytes. But you can shell out to XSD to make that prettier. Or you can just dump a range of addresses using the dump command and then use just any other tool to print out hex dump. One thing that I often do is grep out rows of zeros because that's just blank space. Eye catchers are something you'll often want to look for. In general, eye catchers are a specific case of a pattern that's often part of structures that are allocated. In this case, an eye catcher is something that's put at the top of a structure and makes it easier to identify application allocations. And then this is a deep dive into how to debug malloc itself. There's a global variable if you have the symbols for glibc, mp_, which prints general information, including the main arena, which is that first data segment that it'll allocate out of. And then that has a arena.next pointer, and you can follow that linked list of all the arenas. So that's user dumps. Kernel core dumps, you'll need kdump installed, for example, kexectools, and then you'll need to add crash kernel with a certain size to the command line of the kernel and reboot. You can also control what's dumped with the core collector, and this is all in /etc kdump.conf. And then you simply start the kdump service, and now it's ready to handle a panic. So how does a kernel core dump get created? If kdump is running, you can manually, so if there's a panic inside the kernel, that will start kdump, but you can manually create a core dump using enabling sysrq and then sending C to the sysrq trigger. When the kernel creates a core dump, it essentially loads that memory that we allocated will have another kernel. That other kernel will get loaded, dump the kernel that's panicked, and then it'll reboot the system. So to read the VM core, often as root user, you'll go to var/crash. You can do strings on it to see the version of Linux. You'll need that to match the symbols if you're not on that same system with the debug info or debug sim libraries. So if you do it for the kernel package itself, you'll need those debug symbols. I recommend the crash tool to do the analysis. You can use GDB, but the crash tool is more designed for this, and you can just get it off GitHub and compile. You run crash, and similar to GDB, you pass Linux itself with symbols, and then followed by the VM core. In this case, we run it, and we see the program that crashed, some general information, and which CPU it crashed on. Again, you can type help. dmessage will print the syslog at the time. PS will print all the processes. You could do set to change the context, in this case to a different PID. Or you can set the context to whatever was running on a particular CPU with set-C. Again, stack trace for GTFO. This normally a kernel, you'll have to go to the kernel developers, but if you do bt-l, again, you'll get the stack with line numbers. You can type the VM command to see the virtual memory usage of that process or whatever context you set. Similarly, you see the files that are open. Kmem shows the memory usage, -s for slab for the kernel memory. Run queue shows the CPU run queues. It's a good way, if you're under stress, you can take a core to figure things out. Swap shows swap usage, and RD shows raw memory. bt-f will print the stack contents of each frame. So in this case, proc reg write calls write sysrq trigger. And the way stacks work in general is that if the proc reg write will put the parameters onto its stack when it calls that next function. So in this case, we can do what is on write sysrq trigger to see the function definition. And we see there's a file that's the first parameter, so we could take that first item on the stack in yellow and print it out because we know the structure of it. We can do struct, and it'll print out the contents. What's pretty cool about crash is you can actually load the live kernel into crash. So you can do a lot of this stuff in a live system if you just type crash and you have the symbols. I'll quickly talk about OOM killer. You can use panic on OOM to create a VM core when OOM killer runs. I'll kind of skip swappiness because I'm short on time. Memory leaks, what I normally do is find the largest RSS VMAs and explore those in raw memory. And so to summarize, I think that everybody should set core and file ulimits to unlimited for any programs that they're concerned about. There's multiple ways to do that. And install the symbols for your kernel. And then finally monitor for those core dumps, monitor for the VM cores. And don't be afraid to load the cores, get the backtrace, and find the developer that owns that code. Thank you. Any questions? Here's the PDF if you want. I know there's a lot of info there if you want the details.
So one thing about sending a core to a developer, there could be confidential information in it, so just be careful with that.
Oh, absolutely great point. I forgot to put that in. So a core will have all the memory. So if there's a credit card being processed in some thread, that is in there.
Any advice for when it trashes the stack in the process?
That's tough. Yeah, there are some commands if you look at BT, the man page for BT in the kernel, it has, I forget the argument, but it actually has some built-in attempts to deal with that.
Okay, thank you.
Sure.
If you have the source, you can try compiling with different options. Less aggressive optimization.
Right.
Okay.
If the operating system is hardened, how easy is to dump all of the memory?
What do you mean by hardened?
Well, if you have security configurations in place and the user have minimal permissions, think about a kiosk operating system.
Right, yeah, then you're just getting nothing usually.
Getting nothing.
Yeah, but pretty much the defaults are you get nothing. I think they're pretty poor because we're essentially just continuing whatever bugs and problems there are without investigating them.
And the defaults weren't always that way. It used to be if you had a core problem.
That's right. Yeah, I think it's actually kind of security overreach because we're actually creating a lot of vulnerabilities by not fixing these problems. I understand why the defaults may have changed, but I think it's maybe too far. But I think maybe you do have to be conscious of what you're doing, so that might be why.
I have a question. I don't really understand. So once you have the core dump, you use the tools, and basically you're going back to this reverse engineering, going back to the assembly level. Is that how you can find out exactly what happened?
So in general, you want this. If you have the symbols, you don't have to go to assembly. You'll have human readable stack frames, and that'll usually tell you what's the component that failed. You can go talk to that developer. So that's why symbols are so important.
Okay. And what was that thing about eye catcher? I didn't understand. The developer need to put something on there.
So I think a well-designed program, anytime it allocates memory, it should put as the first 4 or 8 bytes some unique sequence of characters or bytes to help for these types of problems, to catch the eye of a debugger. And this is often not done, unfortunately, and so it becomes difficult to understand leaks and things like that.
Like a magic number.
Yeah, magic number or some set of characters.
Quick one. I didn't know until recently that core dumps are help files. Do you know offhand if IDA can parse them if I just want to see code?
That's cool. I never thought about that. I don't know.
I happen to be working on something that's like a self-modifying binary, and a keyboard hopefully would be awesome for that.
Yeah, that's cool. Yeah, good idea, but I don't know. It does? Okay. Oh, the question was, can IDA read a core dump? And it sounds like it can.
It does.
It does.
Well, IDA doesn't translate to, it's translated to assembly. It doesn't really show, you can't, all I use is do the merge. It doesn't really, you can't go any deeper than, it
Well, if
doesn't translate high-level languages, right?
If you have the symbols, I don't see why it couldn't. Okay, thanks very much.
I have a question. Are you suggesting there's a lot of the dumps might contain vulnerability. I mean, what were you saying?
So the dumps will contain the raw memory. So let's say you are sending a web request, and that includes your password.
Right.
And it's right in the middle of authenticating you, so it's still the password is in memory, then that password will be in memory. Now, it may be pretty difficult actually, because you have to find it on the stack somewhere.
Yeah.
And to understand that piece of memory, it'll be difficult, but it's certainly possible.
Oh, I see.
Yeah, there's actually a customer one time that Switzerland has gotten very protective of sending data out of their country. And so one time, because they got a court on it, was the only way to investigate. I had to go
I see. You had to go
there
to-
just to look, because they wouldn't send it off across the border. So
I get it.
it's actually, I should have added that to the presentation. I forgot.
Okay, great. Now, where did you say your PDF is going to be? At the
Oh.
ToorCon website? I don't know if they.
I don't know if they're putting, but I can send you a
I
link.
think they are putting online, they've asked us.
Okay.
They'll
Yeah,
get
they,
there eventually, yeah.
yeah,
Oh,
did
so
ask me
they
to
do?
email it.
Okay,
I can
all
email
right.
it to you if you want though.
Oh, yeah.
Yeah, that'll be fast.
Yeah.
What is? Oh, is this, okay, hold on a second.
Meanwhile, good talk.
Oh.
We're looking for good people. So.
Cool, thanks.
Really,
Are you hiring
nice
me?
one.
Appreciate it. Thank you.
Okay.
What's your name?
Here.
Near Kevin?
Yeah. Nice to meet you.
Thanks.
You can send me. You know, you can read about the company.
Thank you. Appreciate it.
So let me put a space there. Oh, I never thought about this. This is the first time I hear, where's your space? Where's that talk about core dump?
Yeah, I think what's happened is that the defaults changed to be so restrictive,
Yeah.
and now core dumps have kind of gone away.
Yeah.
And I think that's bad because we're not solving the problems causing the crashes, which I think are often hackers trying to find vulnerability.
That's right. Well, yeah, I tried to steer core dump as a developer. I don't want to deal with it. But
Yeah.
you make a good point. That was a good presentation.
Thank you.